So, are you guys already there? So, can you guys give me a thumbs up if you are now ready? So, one, two, three, maybe around four, 4 out of 11. All right. So, just wait 30 more seconds for the others. Maybe they went to bathroom. So, if you have a question, so you can ask anytime. Okay. So it's like we've lost 3 meetings in total. And that is 12 hours in total. How sad. All right. So let us now finish the number 5. So I hope that you guys are already there. So in here, with the use of nodal method, so let's find the RA or the voltage across RA and RB. Okay. So in here, again, just apply KCL, okay, on those nodes. So we have node A and node B, okay, or node 1 and node 2. So either of those two. So you can use any of those names. But in here, I've used node 1. So the first thing that you need to do is apply KCL. So we have I1 is equal to IA plus I2. Again, going in is positive and then going out is negative. Okay, and then we will use this one as our reference, okay, regarding with our solutions. Okay, so from here we can get I1 by having V1 divided by R1. Okay, so just by using I divided by V, I is equal to V divided by R, then you'll be able to get this formula. Okay, VA divided by RA for IA, and then V2 divided by R2 for I2. And then, all right, so before we go here, we have this one. V1 is actually equal to EA minus VA. So how did we get this one? So again, for the V1, you have to get EA, okay, because we have the given voltage for the EA or G1 generator 1. And then we have to deduct the voltage drop across this one, okay? So that is why we have here EA minus VA. Okay? And the same with V2. We have, where is our V2? VA, wait, let me look for VA. Where is our VA? Voltage A minus voltage B. Hmm. All right, just wait a second. I'm trying to analyze this one. How did I come up with EA minus VA? So V1, this is our EA, and this is our V1. EA minus V1, but why is that VA? And V2 right here is equal to VA minus VE. VA hmm. All right, so I guess I have used a different namings, but for you to be able to get the V1, okay, so since we'll have a given voltage in here, just deduct the voltage across here, which is this one, supposedly, EA minus V1, but I don't know why did I name here VA. Anyway, that's how to solve for the V1 right here. And then the same with V2 right here. So supposedly we have here ED, okay, minus the voltage drop across here. That's why we have minus VB. Okay. Anyway, but seems as I was able to get the correct answer. Okay, so let's just follow this one for now. But supposedly that's how it goes for this one, for the V1 and then the V2 right here. Okay, for those two voltages. So just substitute those given equations, and then you will get this one. And just simplify those terms. I guess you can easily analyze this one, just by simplifying this one a little more or expanding it. And then rearranging the similar uh, numerators wherein we have three VAs. So from there, we can have this equation. Okay, just uh, put it outside. And then you can now add those variables, R1, RA, and R2, since they are already given in our circuit. Okay, and then from there, you can simplify this one a little bit more, okay, wherein you will get 17 divided by 3. And for the EA and R1, so they are already given. So just substitute their values, and then you will get 800 for this one. And then the VB minus divided by 0.5 is still the same. Okay, and then from there, what did I do? All right, so I didn't do anything anymore. I've just arranged them, okay, into this kind of arrangement. So we have the VA right here, and then the VB right here, and then the third value is now on the other side, which is positive 800. Okay, and then using nodal method 2. So again, on nodal method 2, just apply KCL again. So we have here I3 is equal to IB plus I2. Is it I2? IB is equal to I3 plus I2. All right, so anyway, they are the same. So I3 plus I2 or plus I2 plus I3. Okay, so we have this one. So this is the one that we need to follow, okay, by using again the formula of Ohm's law. I is equal to V divided by R. And by having those values in here, the V2, okay, is equal to VA minus VB. Okay, just substitute those and then you will get this one. All right. And then from here, you can arrange everything again, or you can expand everything. So we have substituted the given values and then simplified it. Okay. And then we've just added, or we've just arranged the similar variables, which is the DP right here, so that we can add whatever we have in here. So you will get 1096 divided by 120 for this one. And negative VA, what is one? This one right here. So we didn't do anything in here. And then this one is still the same. We didn't also do anything. Okay, we just arranged them. And then you will have this one as a simplified equation, okay, once you have solved everything. And right here, minus VA. Okay, so I just arrange them. So we have the VA right here, and then the VB, and then the third value. Okay, so this is now the equation number 2. So from here, we already have the equation number 1 and equation number 2. So you can use simultaneous equation, or you can. All right, so there's no other way, I guess. So the easiest way is by using simultaneous equation by eliminating one, okay, or just come up with another equation wherein forming VA is equal to the other expression so that you can substitute that value of VA onto the equation number 1 or equation number 2, okay, with that newly created equation. But in here, what I did is, I see. So I thought uh, uh, I use the simultaneous equation, but the one that I use in here is, to come up with another equation wherein, oh, sorry, what do you call this one? Binabawi ko yung sinasabi ko. Okay, I retrieve what I have said. The one that I really use is simultaneous equation. So I thought that I have come up with another equation using those equation 1 and 2, but it's not. Okay, so I've just removed or I've just made it more simple, by multiplying and dividing the numbers right here. So we can eliminate the values for VP. So in that way, we can easily remove the VP. Okay, so in here, I just, made a way so that I can have variable VB only. So the same with equation number 2. So I eliminated this one by multiplying 123 divided by 1096. So in that way, we'll come up with VB and VB only. So from here, we can already use simultaneous equation. Okay, so just add, and then you will get this one as a value for not yet. Okay, so you will get this expression. Okay, and then from here, you can already solve the VA since we now only have one remaining variable. So the one that we've got here is 227.90 if we have this value right here, or 228.7 if we have this value right here. So since we already have the VA, then substituting the value of VA on equation number 1 will give you this result. 248 volts and 247.90 volts. So I dropped those two. So the answer that we have in Canvas is 247.98. But in here, I've got a different answer, which is 248, wherein we are super close. I guess the one that I have used last year, okay, is maybe one decimal only or 0 decimal. That's why I have got a different answer instead of always getting the 2 decimal. Anyway, so those are the solutions for your midterm exams. So I hope you guys were able to follow my solution. So again, if you guys are confused in some part, so let me know so we can discuss the part on how did I get that equation or that expression. Okay, so any questions so far before we end the review or the discussion regarding with your midterm exam? Question, guys, or clarification? So that we can now proceed to our next example. Mr. Gangas, Miss Michael?
Wala naman,
Mr.
sir.
Ivo? Mr. Bautista? Mr. Masvela? Jennifer?
Wala po, sir.
Dulay, okay. Mr. Eric Jan? Mr. De La Cruz? Santa Cruz? Sure? Okay. So if you guys don't have a question anymore, then let's now proceed to the next topic. All right, so Norton's Theorem. So I'll make this one as quick as possible. Okay, so for the Norton's Theorem, okay, so this one is actually applicable in all of the circuit as long as you have a load resistor wherein you want to solve a specific component that will not change. So basically Norton's Theorem and Thevenin's Theorem are like uh, twins, okay, or sisters. Twins na lang. Okay, kasi talagang sobrang close sila. Okay, you can say that they are twins, that there's only one that they have when it comes to there's only one that they are differs when it comes to comparing things. But you will always come up with this kind of simplified circuit. Anyway, so let me just recall so that we can compare the Thevenin's theorem. So in Thevenin's theorem, where is that equation? Okay, so in Thevenin's theorem, you will have a series connection, okay, wherein you will get the Thevenin's voltage and then Thevenin's resistance. And then we always have this one, the load resistance, okay, which is the same with the Norton's theorem. It's just that in here, so it says here, simplify any linear circuit no matter how complex the circuit is. So to an equivalent circuit with just a single current source and parallel resistance connected to a load. So in Thevenin's theorem, we have a voltage source, but in Norton's theorem, we have a current source. Okay, so that's the only different thing. And the connection. Okay, so the Thevenin's theorem, we have a series connection. So we have here the resistance. But in Norton's theorem, we have here the resistance. So we call that one R Norton, okay, or Norton's resistance. And one more thing for us to be able to compare the Norton's theorem and then Thevenin's theorem. So we are also using the same example. Okay, so we have 28, 4, 2, 1, and 7. And then we also have, oops, yeah. So this is for the Norton, and then this one is for the Thevenin's theorem. So they are the same, 28, 4, 2, and then 1 and 7. So yeah. All right. So in here, we have to come up with this kind of circuit. Okay. So if you guys can still recall, okay, we have 4 steps or 3 steps for us to be able to uh, have this kind of circuit. So the first thing that you need to do is get the I source or I current, okay? And then the next one is the R Norton or the Norton's resistance. So how are we going to come up with that one? So again, similar with the Thevenin's theorem, we have to identify where the load is and then again remove that load resistor. Okay, so first step in Norton's and Thevenin's, so they are the same. And then close that one. Okay, once you have removed the load resistor, you have to short the connection, wherein in Thevenin's theorem, it is the exact opposite. Okay, so in Thevenin's theorem, you have to leave that one open. Okay, but in Norton's theorem, you have to short circuit this one for you to be able to find the current. Okay, so to find the Norton current, uh, for the current source in the Norton equivalent circuit, place a direct wire short connection between the load points, okay, which we already did. And then from there, you can already solve the current that is flowing in this short circuit, okay, or short wire. So how did we get this 14 amps? So again, let me just copy this one. Okay, so from here, okay, so just apply Ohm's law. We have I is equal to V divided by R. So we know that we have a current that is flowing here, current that is also flowing here. So they will meet in here having the same uh, direction. So that's why they will be added with each other. Okay? IR1 plus IR2. Or you can just simply apply KCL in here. Again, going in is positive. Going in is positive, and then going out is negative. That's why we have I short as negative root. And then you will come up with this kind of solution. So again, just apply Ohm's law. So for you to be able to get the current in here, the I1, okay? So R1 or I1 is equal to V1 divided by R1. So V1 is 28 volts, and then R1 is 4 ohms, wherein to give you 7 amps. Okay? That's our I1. For the I2, so the same, we have V2 divided by R2, okay? R3, rather, sorry. So we have here 7 volts divided by 1 will give you 7 amps, okay? So 7 plus 7, okay, will give you 14 amps, okay? So that's how we've got that value. Okay, so were you guys able to follow on how did we get this 14 amps right here? The supply Ohm's law.
Yes, sir.
No? All right.
Yes, sir.
So thank you for your... Kala ko wala na kayo eh. All right. Okay, so where is my cursor? So that's how we've got 14 amps. So whatever is that current that you have solved in there, that's already your I Norton. Okay, so we call that one Norton's current. Okay, so let me just close that one. And then from here, so that's how we've got the I Norton. So we already have this one. So now the next thing that we need to do is find the R Norton. Okay, since I've mentioned a while ago that the process is super the same, it's just that here we have to find the current instead of the Thevenin's voltage. So in looking for the resistance, okay, the resistance on this load resistance is also the same. So having this one, okay. So if you're going to uh, go back with our Thevenin's theorem, this is node A and node B. So having that in mind, we have this representation. This is the node A and node B. So as you guys can see, they are in parallel with each other, the 4 and 1. So we cannot say that they are in series because we have a node in here. Okay, and this is where we are trying to solve or get the final value of your R Norton, okay, or Norton's resistance. Okay, so from here, just apply uh, parallel, okay, connection R1 times R2 divided by R1 plus R2. So 4 times 1 divided by 4 plus 1. So we will give you, oops, 4 divided by 5. Sorry for my handwritten. Well, we are doing this real quick so that we can finish the next module after this. So 4 divided by 5 is 0.8, which is now this one. Okay, so just apply the parallel connection between those two. So are we clear with this one on how did we got the 0.8? And if you guys are going to go back with the Thevenin's theorem, they are the same, which is 0.8. Just apply parallel connection or parallel solution. Okay, so once you guys have already solved the not Thevenin's, Norton's resistance and then the Norton's current, then you can now form this circuit. Okay, this is not equivalent, oops, equivalent circuit for the Norton. So the next thing that you need to do is find the voltage across the resistance. Okay, so so we will not use this one since that one is quite confusing. Let's just get this one and then solve that in our own. Anyway, are we clear with this one on how did we get the R Norton? No guys, R Norton. Yan pa ba kayo? Sure. Okay. Mr. Santa Cruz, clear down. How about Mr. De La Cruz? Mr. Dulay? Mr. Sagibo?
Clear, sir.
Okay. Sure kayo ah. Again, just apply a parallel connection with this one and for you to be able to get the 0.8. All right then. So let me delete that one and let's now solve the voltage across the voltage across your load resistance. And then we also have to find the total voltage. So from here, we already have the I total, okay, which is 14 amps. The one thing that we don't have is the V total. Okay? We also don't have the R total. So for us to be able to get the V total, so we need to have the R total. Okay, so R total right here is actually super easy. So they are in parallel. So just multiply that one, 0.8 times 2 ohms divided by 0.8 plus 2. So from here, you will get 1.6 divided by 2.8, 1.8 divided by 2, 1.6 divided by 2.8. So we will get here 0.571. All right. So we already have the total resistance. So now we can now solve for the V total. So V total is equal to 14 amps times 0.571 times 14 will give us a V total of 8 volts. Okay, so that is the voltage on this entire circuit, okay, or the voltage across R2. So yeah, that's how we've got the V total using ohms law only. So very, very simple. So Thevenin's theorem, Norton's theorem, is basically ohms law. Okay. So are we clear so far? And how did we get those values? So again, whatever is the voltage across this point, so they are just the same since they are in parallel, 8, 8, 8, 8. And then here are their individual currents. So we have a total currents of 14. And then we have a current here for 10 amps and then 4 amps right here. And for the resistance, so we've got a total resistance of 0.571 or 571.43 milliamps. Milliohms rather. Okay. So are we clear, guys, regarding with this one?
Clear, sir.
Okay. Again, just look for the R total, and then you can now find the V total. Okay, so if you guys have a questions, just let me know. So we now only have 7 minutes. So here's the review. So again, just remove the load resistor. That's the very first step. And then look for the Norton source or the Norton's current. And then once you're done in finding the Norton's current, then you can now look for the Norton's resistance, okay, by removing all the power sources. So basically, this one is the same with the Thevenin's theorem. It's just that it has a different name, which is Norton resistance. So once you're done in finding the Norton source and Norton resistance, then you can now you can now convert the entire circuit into equivalent circuit of a Norton circuit. Okay, and then you can now analyze the voltage and then find the unknowns, the VP, the IP, and then the IP. All right, so we have another example here, which came from another website. Basically, they have the same, call this one, the same schematic or the same layout. Okay, we have voltage here, we have the resistance right here, but just at different values. So I will leave this one to you guys. Okay. Anyway, we have the solutions right here. And how did we get those values? So again, just short this one. Okay, since this is our load resistance, the 40 ohm load resistor, and then find the current. Okay, so the current for I1 and I2. So we have 1 amp, 1 amp. So a total of 2 amps for the Norton's current. And the next one here is the Norton's resistance. Okay, just remove that one again and then solve the total resistance regarding with this one. Okay, so just uh, solve this one in a parallel. Okay, and then you will get 6.67 ohms. So right here, you already have the 2 amps and then the 6.67 ohms. And then you can just simply plug here the 40 ohm resistor, okay, which is now this one, the load resistor. Then from here, you can now find the R total, and then you can now find the V total or the VA. Okay, so I hope that you guys were able to follow this one, since this one is just the same with the past examples or with my example above, just a different value. Okay, and the total current is 0.286. I mean, not total current, the current that is flowing on that load resistance. Okay, IT, which is so. And we have here videos. Well, you can find these links already on the canvas. So I have put in there the links for the tutorial. So we have the English version and then the Tagalog version. So again, as a summary, just remove the load resistor, and then you can find the RS. So either of those two, the RS or IS, so it doesn't matter. So you can solve any of those two, okay, without even solving the other one. So once you were able to find the RS and IS, then you can now convert that one into its equivalent circuit. Okay, and you can now find the current flowing through the load resistor, or the voltage or the total voltage on that circuit. Okay, and yeah, so far that's it for the Norton's theorem. So if you still need to look for another website, well, this one right here, the above example came from All About Circuits. And then the next example here came from, if I'm not mistaken, this one came from Neso Academy. Let me see. Electronics tutorials. Okay. So the first one came from All About Circuits, and then the second one came from Electronics tutorials. So if you want to explore more when it comes to Norton's theorem, you can visit this one, circuitglobe.com. Okay. So yeah, that's it for the Norton's theorem. And the next one will be source transformation. Okay, so any questions so far? So what is the part that you guys were confused? No, guys? Question or clarification? All right. So just an advice, since this is already your last quiz. So make sure to review Norton's theorem. Okay, because you guys are going to have a quiz for the Norton's theorem. So let me just edit this one. Okay, so the due date is until April 15, so you guys have plenty of time. So make sure to visit those links for you to be able to practice about. Oops, my bad. So these three are only about Thevenin's theorem. So I will add some links later on. But mostly you can find some good examples from this website, sunfoundry.com. Okay, so they are one of the most easiest website where you can practice. Okay, so it will give you the complete solution, a very simple circuit for you to be able to master the basics. Okay, so make sure to check your websites. Anyway, so that's it for now. We'll just continue the next topic on the part 3. So goodbye and see you guys later.
Bye, sir.
Goodbye.
Thank you, sir.
Thank you then.